Here we're looking at 6.1, the standard normal distribution. The standard normal distribution is the distribution of z-scores. It is the normal distribution that has a mean or mu of 0 and a standard deviation or sigma of 1. Since z-scores are often used in research and medicine, it is useful to find probabilities associated with certain z-scores. It is also useful to find z-scores that are associated with certain probabilities or percentiles. So here we're going to look at bone density. So we have a bone mineral density test that can be helpful in identifying the presence or likelihood of osteoporosis. The result of a bone density test is commonly measured as a z-score. The population of z-scores is normally distributed with a mean of 0 and a standard deviation of 1. Find the probability a randomly selected adult has the bone density z-score less than 1.27. We're also going to look at a person is considered to have a healthy bone density if their z-score is above negative 1.00. What is the probability a randomly selected adult has a healthy bone density score? And number 3, in a group of 35 randomly selected adults, how many of them will have healthy bone density? So since bone densities are measured in z-scores, then we know the following about the bone densities. They are a normal distribution, so they're bell-shaped, and since they're measured in z-scores, they have a mean of 0 and a standard deviation of 1. And this is where that standard normal distribution comes into play. So to find the probability that a randomly selected adult has a bone density score below 1.27, we need to find the area under the normal curve to the left of 1.27, when, of course, our mu is 0 and our standard deviation is 1. And so see here, I have my normal curve already drawn to the right and shaded to the left where our z is 1.27. Now, if you want to work with just that norm.dist formula that we did in section 6.2, you're just going to be putting in a mu of 0 and a standard deviation of 1. But I do want to make sure that everyone knows that there's also a standard normal distribution formula. So you could just use that and you would enter norm.s.dist, your z, and then true. So in this case, it would be norm.s.dist, parentheses, 1.27, comma, true. And when you put that into Excel, you should get approximately 0.8980. In number 2, we are looking for the probability that a randomly selected adult has a bone density score. So we're going to need to find the area under the normal curve to the right of negative 1. And this is because any adult that has a bone density score of above negative 1 is considered a healthy bone density. So if I go ahead and start marking off those pieces that I need, okay, so I have my area here, I'm drawing and above negative 1, so we're shading up this way. Okay, now you have to keep in mind that Excel does not find areas to the right, it only finds areas to the left. So what you're going to need to do is the complement rule, okay? So you'll need to find the area actually to the left and then subtract. So you're going to do norm.s.dist, and then we've got negative 1 true, and that's going to give you 0.1587. But to find the area to the right, you're going to do 1 minus 0.1587. And that's going to give us approximately 0.8413. To find the number of people we expect to have healthy bone density out of the group of 35 randomly adults, we are going to multiply the probability of a healthy bone density by 35. So remember, we got the probability that the z is greater than negative 1 as 0.8413. 0.413 in the earlier problem of number 2. So now all we do is take that probability and multiply it by 35, and we get approximately 29.4. So we are generally going to expect about 29 people out of 35 to have healthy bone density. So we did finding the probabilities. Now if I want to find the actual scores. So just like in 6.2 where we used a norm.inverse, there's actually a norm.s.inverse formula that we can also use. So let's look at an example here. The head circumference of an infant at birth is approximately normally distributed with a mean of 0 and a standard deviation of 1. A certain study is interested in infants who have very small head circumference. The researchers want to include infants in the study who have a head circumference z-score at or below the 5th percentile. What is the highest score that would be included in the study? And number 2, a parent is informed that their child has a head circumference z-score in the top 20th percent of all infants. What z-score separates the top 20th percent? So to find that z-scores for the bottom 5%, you're going to go ahead and just remember, I'd always start with, sketching that normal curve, drawing that area. Okay, so I'm just kind of sketching here. So that blue squiggle, that's not going to be my 5%. You are looking for this, I'm going to call this a value. So we're going to go into Excel and we're going to type in norm.s.dist. Again, you can use norm.dist. You would just need to actually type in the mean and the standard deviation then, where in this one you don't have to do that. You can just do your norm.inverse and your norm.s.dist, and you'll just be typing in the probability. So for this case, it's 0.05. Okay, and when you type that in, you get negative 1.6449. So the highest z-score that would be in the study is negative 1.6449. And then number 2, we're trying to find the B that cuts off that 20th percent. Okay, so I'm going to come over here. We're saying, what is this B value? So you have to remember, if this is 20%, then this down here is 80%. Okay, so our probability is going to be 0.8. So I'm going to go to Excel and do norm.s.dist 0.8, and then you should get 0.8416. So the child's z-score is at or above 0.8416. Standard deviations higher than the mean. So you can see that 6.1, using that standard normal distribution, is a lot like 6.2. We can either use 6.2 formulas and then type in a mean and standard deviation of 0 and 1, or we can use that norm.s.dist or norm.s.inverse. Your lab manual pages here to practice are pages 51 to 52. And of course, you have your My Stat Lab homework, section 6.1.